In this session, we are talking about a few important mathematical functions in R. So, wherein we would look at the most commonly used functions as a part of various applications, right? We require logarithmic functions. Something log is a kind of a R function that can help us to perform logarithmic. In the introductory part, we'll try to understand what are the important functions that I'm supposed to know if I have to really work out with the data. We need to understand trigonometric functions, how to solve trigonometric problems using R, then power related functions and power related laws. Then we'll move on to understand polynomial functions like quadratic, ax squared plus bx plus c kind of forms, quadratic, cubic, they all will come under polynomial functions. Then a few important functions that are worth understanding, one being a gamma function, right, which has a specific meaning, which has something to do with the factorial as well. So we will understand the gamma function. Sigmoid functions, which are typically S-shaped functions, which are generally used for cumulative probability distribution functions, and even for a few specific density functions, we observed that their cumulative distribution functions are more sigmoid functions. Then we'll talk about bi-exponential model. So for all these, we'll have a quick plot of their graphs to understand how they typically look like. What is the shape of the graph? Is it a kind of an increasing function, or is it a kind of a decreasing function, or do we see some kind of humps? So what would be the typical shape of each of these functions? Even that is something that we would be understanding. And towards the end, just trying to understand a couple of important functions from the world of mathematics, especially to do with permutations and combinations, which are helpful for us in doing probability related computations more comfortably. So we would look at those aspects on a very broad kind of a perspective. So we know a few important structures of the variables. If my variable is raised to the power of b, this could be one kind of structure where my variable is there as a base, and some exponent it is raised to. So probably you'll have it as x squared, x cubed. These are all polynomial kind of stuff. X power half, which is square root of x, cube root of x, etc. So these are some kind of structures that we can see with the data. Then we'll have something which is raised to the e to the power, which are more of exponential kind of functions, e to the power of something. Then similarly we'll have a few functions wherein we express them as logarithm, which is nothing but the inverse of the exponent. We know that if e to the power of x is equal to b, then it means that x equal to logarithm of b. So that's how we define the relationship between the exponent and the logarithm. Some of the basic rules which I don't want to, which I don't need to explain in depth. Anything raised to the power of 0 is 1. 1 raised to power of anything is 1. Any number added or subtracted from infinity is still an infinity. 1 by infinity is 0. Anything raised to the power of infinity is infinity as long as that value is greater than 1. Any value that is greater than 1 raised to the power of infinity is infinity. Any value that is less than 1 raised to the power of infinity is 0. Then a variable raised to a negative power is nothing but 1 by variable raised to that particular the positive power. And similarly, a variable raised to a fraction is nothing but the nth root of that particular fraction. And we also have a few more things. Anything raised to the power of infinity is infinity as long as it is greater than 1. Anything raised to the power of minus infinity is nothing but 1 by the same value raised to the power of infinity. If it is greater than 1, 1 by infinity will become 0. Some of the very basic laws of mathematics that I expect every one of you to be comfortable with before we start operating anything on R. Now, looking at some of the important functions, now let's start applying one by one to the R scenarios. Logarithmic functions, if I have something y equal to a log x, right? I have y equal to a log x. So the logarithm here, we are always defining the logarithms to the base e. E is typically your 2.718, which is nothing but 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus and so on up to infinite. This would narrow down to, this would converge to a value called E, which is otherwise equivalent to 2.718. Now let's take the graph of e to the power of x for different values of x, right? And similarly, we can take logarithm of x where we can see both of them are inverse of the one another. Okay, so let me take the r. Let's take the x values from 0 to 10. So I'll take the x value from let's take it from 0 to 10. So y, let's take e power x. Y e power x, I'm using the function called e. So 0 to 10. Let's take it with or let me take a very small gap. So I'll put a sequence from 0 to 10 with 0.1 as a gap. So yex exponent, I'll take it as exp of x. Then I'll plot x and yex. So when I'm plotting x and yex, and probably let me take it as a type equal to line so that I'll get a good line curve rather than a set of points. So this is how the y equal to e power x graph is coming up. Right? Do I have any explanation? So it is more and more of exponential growth. Right? This is the graph that I am getting for e power x. It's an indication of exponential growth in the data. So initially the growth is very marginal, but as the time is progressing, the growth is charging up like anything. That is how we look at an exponential function. On the same lines, I can very well go ahead with y log x. Let me look at y log x kind of a function, right? So let me call as y log x, wherein I am taking it as logarithm of x. Now let me try repeating the same plot x comma y log x type equal to L. So this is how I'm getting my y log x kind of a function. So for log 0 I am getting something like minus infinity, and as it is increasing, as the values of x is increasing, I see that the log x is typically keeping on going up, but after that it is stagnating much and much. So that is where I could see the log x curve. Initially it is zooming up like anything, but after that it is stabling out. So that's how you look at the logarithmic function. So if I am talking about a decay kind of a step, I can focus more and more on the logarithmic. If I am looking at an exponential growth kind of thing, I can very well look at a logarithmic. So both of them, one is the inverse of the other. We can see how these two things are typically getting shaped up. Then the next set of functions, right, apart from logarithmic and trigonometric, the next set of functions where we should get some level of understanding are the trigonometric functions. General trigonometric, there are 6 functions we know: sine, the cosine called as cos of x, tangent called as tan of x, So we know in a right angle triangle, right? If I'm looking at it from this particular side saying this is x, this is the opposite side, this is called as the adjacent side or the base, and this is called as hypotenuse. So the sine of x is nothing but the opposite side by the hypotenuse. Cos of x is nothing but adjacent side divided by the hypotenuse, and the tangent of x is nothing but the opposite side divided by the adjacent side, which is otherwise sin tan of x is nothing but sine of x divided by cos of x, right? And the inverse of this 1 by sin x is called as cosecant x, 1 by cos x is called as secant x, and 1 by tan x is called as the cotangent or cot x. So these are some of the common names that are there, used very heavily in trigonometry. All these values range from, I can try looking at the graphs of all these things in the range of 0 to 2 pi. So I can very well create all these graphs together. So let me create par mf rho. So let me take it as 2 comma 2, so that I'm splitting the plot area into a 2 by 2 area so that I can plot 4 charts altogether. Now I require the values from 0 to 2 pi, right? So let me set x as a sequence from 0 to 2 pi. 2 into pi is 2 pi here, and I want to give a gap of, so probably let me take it as pi by 100, right? Each take as an interval of pi by 100 each of the values. So these are my values of x. Now corresponding to the x, I'll take y sine as nothing but sine of x. I'll take y cos as cos of x, and I'll take y tan as tangent of x, and I can also take y cosecant as 1 by sine of x. I'll also take y secant as 1 by cos of x, and I'll also take y cot as 1 by tan of x. So I can very well do the plotting for all of them, right? It would have been better if I had taken it as 2 by 3 kind of a par. So let me, that's where change it, mf rho equal to c 3 comma 2, 3 rows, no, I'll set it as 2 comma 3, 2 rows 3 columns. Okay, so now I'll do a plot x comma y sine, wherein I'm setting the type equal to L. So this is how I'm getting my sine curve. Now I'll set it as, if I want it as cos, I'll put it as x comma y cos, wherein I'm getting my cos curve. So this is how my cos curve is coming between 0 and 2 pi, ranging between 1 and 1 going towards minus 1, and that's how the cos curve is coming. Similarly, I can very well do it as tan, right? I'll take it as y tan, which is giving me my tangent. Here I am seeing some kind of gaps in the curve. So y tan is coming out as tan of x. The tangent is getting prepared in this way, right? Because we are going with 0 to 2 pi. Okay, the y tan is coming out to be more like this. Then I can have y cosecant. So y cosecant is coming as 1 by the sign. Let me take x values first of all. The x values, there are 200 of them, and if I am looking at tan x, also in tan x I am getting a slightly more number of observations. X I am getting 201. Tan x also I am getting 201 values. And when I am plotting, let me take it on a single screen itself. For mf row 1 comma 1, so that let me observe it. Mf row equal to c1 comma 1. Now let me plot x comma y tan. So this is how my y tan is coming out. Right, the interval is having a problem, so let me set my interval. So y lim, it's better that I set my interval y limit. Let me set it as between -1 to +1. Then I'll get it very clearly. Right, so this is how my tangent curve is typically coming. Similarly, I can go for cosecant. The same logic, instead of y tan, I'll go with y cosecant, which is giving me that the curve is somewhere here and somewhere here, just above 1, below 1 kind of, below -1 kind of stuff. The same thing goes with secant, which is also lying between, here it is 1, here it is 1, here it is below -1. And the cot also goes exactly opposite to that of tan. So these are the different kinds of trigonometric functions that we need to be comfortable with. We should be able to plot these kind of trigonometric functions. So you have to define the limits appropriately so that the graph can be plotted more comfortably. The same tan function, you set the limits not between -1 and 1, set them between -3 and 3, you get a slightly much better kind of a curve. So depending on how you are selecting your limits, your graphs can get plotted more and more appropriately. So, but you need to have some kind of an understanding regarding the trigonometric functions and how each of these graphs look like, so that once you are looking at your data, you would be able to map them to the appropriate distribution. Then, the next important aspect that you need to be comfortable with are the power related functions. So, where your functions are in the form of y equal to ax power b, right? So ax squared, x cube. So those are all power related functions. So depending on the value of the power of b, if it is greater than 0, you will find some kind of functions. If it is less than 0, you will find some other kind of functions. The shapes will actually differ based on the value of b. Whatever is the value of a, depending on how the value of b is, we'll find different shapes. So just look at x typically having values between 0 and 1, right, with 0.01 as a gap. Then y, right, let's talk about different kinds of y's. So let me plot x comma the y here. Let's say I'll take it as x to the power of 0.5, something less than 1, and let me set the type of it to line. So if my power is less than 1 or below 0, between 0 to 1, the kind of graph that I am getting is more like an increasing kind of a graph. If my power is between 0 and 1, you can try repeating it. Right, you can try repeating it, let's say with 0.8 also, you'll get more and more similar kind of a graph. But yes, the lesser it is or the farther it is away from 1, you'll see that it comes more and more curved, which would more or less, shape wise, it would more or less resemble a log x kind of a graph. But of course, log x will have a value which are very negative for values much lesser than 0. But here only the shape looks more and more from that perspective. So the more and more your power is closer to 0, between 0 and 1, you will find it more and more steeper like this. But if you are seeing the value to be exactly 0, then it's a straight horizontal line. But if the power is slightly increasing from 0, let's say zero point 0.1, you'll see more and more such kind of an upward sloping line. Up to some point the steep is very high, and after that it flattens out. But the moment this value touches close to 1, you'll see that it becomes more and more a straight line. And the more and more it goes above 1, let's say I'm setting it to 2, then the curve starts the other way. Initially, so the exponential kind of a behavior starts coming up. If my power is going much higher and higher, the exponential behavior will start piling up. Right? So the more and more the value is going below 1, so between 0 and 1 going close to 0, you will find initially the steepness is much higher, and after that it flattens out. Whereas if the power is going much higher, initially the flattening out happens for the graph, and after that it starts exponentially growing up. So those are some of the things that you will observe. And the moment you see the numbers are more and more less than 0, right, instead of setting it as 10, set it as minus 1. X to the power of minus 1 is 1 by x. So you will find it exactly in the opposite way. Initially there would be a steep fall, and after that the values will stable out. So that is how we are seeing an exponentially declining kind of a stuff, a decay kind of stuff is plotted with your powers to be around negative powers. So these all kinds of graphs can be very well obtained the through the power related functions itself. You have so many applications for different kinds of data. You will observe different such kind of patterns coming up. And there's one more important thing that we need to understand in this context, which is the Taylor's power law, which has so many applications in a wide range of statistical analysis. So there is some kind of a relation that is generally defined between the variance and the mean of any sample. In many models, we really make an assumption that the variance is assumed to be constant. Whether we are talking about the regression model, a very general regression model, or we talk about very elementary ANOVA kind of models for doing our data analysis, we assume in all these cases the variance is constant. But in the real world, we may not have the data following this kind of an assumption. What we generally observe is the variance keeps increasing with the mean as per the power law. So as the mean is increasing, you will find that the variance is also going up in the data. So the variance to the mean ratio is also not constant. The variance is not really coming out as constant here. It is increasing according to the power law. And what is generally observed is when I take the logarithm of the variance and I take the logarithm of the mean, in that case they are found to be more and more linear. But mean and the variance only if I am taking, they are not linear. They are increasing as per the power law. That's the real world data. That is what again the application of the Taylor's power law coming into picture. Right? When I take the logarithm of the variance and I take the logarithm of a mean of a data, I'll find that the function is more and more linear. And when I'm saying the function is linear, the errors around that particular line are much smaller compared to an errors that are coming when I'm plotting the mean and the variance. So you will see a lot of applications as we move further along where power laws are used very heavily in practice. So understanding of the different shapes, how the x squared looks like, how the x cube looks like, etc. is also very much essential for us. Then comes a more where I am combining, which we are calling as polynomial functions, right? Y equal to x squared is a quadratic, or more generic form ax plus b is a linear function. Y equal to ax squared plus bx plus c is a quadratic form. So similarly you can have cubic or any other polynomial form typically coming into picture. So the polynomial functions are y equal to ax plus b, y equal to ax squared plus bx plus c. All these things come under the polynomial. So here we see the x is appearing several times. These are called as your polynomial functions. Each is raised to a different power. In which case it is raised squared, it is raised to the power of 1 and so on. So these kind of functions are typically called as your polynomial functions, and depending on the different kinds of values you are giving, you will get different such kind of shapes in case of polynomial functions. Probably what you can try out is, let's try a few important functions. Let's say I'll call y1 as 2 plus 5x minus 0.2 x squared, and after that you try increasing this 2 plus 5x minus 0.4 x squared. So this is your quadratic kind of polynomial, but this value of x squared going more and more negative. Or you can try out a graph which is zero point 0.4 x squared plus 5x plus 2, which is more and more positive, all the variables. Then you can also try out another curve where we are talking of the fourth degree or cubic 0 0.4 x cube plus or probably plus or minus 0.6 x squared plus 4x plus 2. Some such kind of graphs. So these are your regular polynomials, quadratic, cubic. In some cases I can also have my inverse functions, x by 2 plus 5x. Right, I can even have some things as a part of my inverse also. Y6, I can call it as 1 by x minus 2 plus 4 by x. Some such kind of function. So if I start plotting all of them, there are different kinds of shapes that are coming out for each one of them, and a good understanding of each one is very much important for me, because depending on the kind of a data, I can very well see what is the kind of shape that it follows. I can try mapping the data to that particular shape. So let's try plotting all these graphs one by one. So in R we can create a 2 by 3 kind of a matrix for the output, and we'll try to plot all the 6 within this 2 by 3 window, where each graph would be plotted. We have 3 rows or 2 rows of graphs, each row containing 3 different graphs. So that's the kind of plotting that we can very well do to understand the shapes of each of these different polynomial functions. All right. Now let's quickly look at creating these plots, right, for each one of them. So let's put par mf row equal to c2 comma 3, and here let me do a plot. Right, I'll do the plot of, so I'm taking x values. What is the x I'll take here? X values I'll take from 0 to 10. Alright, so 0 to 10 with a gap of 0.1 is what I'll take for x. So let me compute a few of them. Y1, I'll take it as 2 plus 5 times x and minus zero point 0.2 times x squared, that is y1, right? And I will plot x comma y1. So this is how x comma y1 is getting plotted. And similarly, I can very well take my y2, right? Let me increase from, let's say, instead of minus 0 0.2 x squared, let me make it as 0.5 x squared, right? I'm increasing the negative, which is the decreasing the value of the x squared coefficient. And in this case, when I'm doing a plot of y2, I see that there's some kind of a hump that is getting covered. Similarly, if I make it more positive instead of negative, if this becomes positive, and for this if I plot my y2, it comes more as an increasing function. Similarly, if I keep adding cube, right? So let me put a minus out here for square, but let me add let's say 0.4 x cube. So you will find, okay, zero point 0.4 into x cube multiplied by x cube. So now when I'm doing a plotting of x and y2, I'm getting something like this, but for x cube you can very well find a kind of two terms, right? Depending on the value of the x, we can get two different terms depending on the values of x. So I can think of, if I take, let's say, x minus 1 into x minus 1 into x minus 3. So let me take it as y2, let me take it as x cube, right, minus 6 times x squared plus 11 times x minus 6, right? If I say is this, and let's say I'm plotting x and y2, so this is what I'm getting for my values of x cube minus 6x squared plus 11x minus 6. So for different values of x from 0 to 10, we get shapes of different kind. Similarly, I can very well plot my inverse functions as well. Let's say I'm saying 1 by x minus 2 plus 4 by x. The same y2, I can very well make it as 1 by x minus 2 plus 4 by x. So in this case, when I'm doing a plotting for x and y2, I'm getting it this way. So what you could see is polynomial functions, they show some kind of curves. So these are like my local maximas and minimas at different points. So they are very much useful for defining the curves with humps, local maximas and minimas and inflections. So when we are trying to plot different kinds of quadratic, cubic, inverse functions, we see these kind of behaviors coming up in the data. So wherever we see such kind of behaviors cropping up in our real world data pattern, we should see that can we attribute some level of polynomial functions to those kind of data points. Then once we are comfortable with the polynomial function, the next thing we need to be comfortable with is a gamma function. Typically, integral form of a gamma function looks like it's a summation or the integral from 0 to infinity e to the power of minus x, x to the power of t minus 1. So if I am integrating this particular value across 0 to infinity, that is what I am calling as a gamma function. So it's an extension of the factorial function, because we will find gamma of t. If t is an integer, it will become t minus 1 factorial. So that's the reason I am calling it as an extension of the factorial function, especially to the positive real numbers. So for integer values of t, gamma t plus 1 will become t factorial. But I can very well compute the gamma of t directly using the gamma function. Right, so probably if I am saying gamma of 0.5, it is 1.77. I can say gamma of 5, then it will be 4 factorial, which is 24. So now I can take my x values as a sequence between 1 to 10 with an increment of 0.1. Y I will take it as gamma values associated with x. Then I will do a simple plotting of x comma y, which will give me that the gamma function is more or less flat, right? Initial values are much lesser, but the exponential jump is going to be much higher. That is the kind of a difference we see with respect to gamma. Just like your factorial function, the factorial function also keeps going up, but it is defined only for your integer values, whereas the gamma function I can have it defined even for non-integer values as well. But after a certain point in time, you see a steep rise in the gamma value. But until a particular point of time, the gamma value is more or less increasing at a marginal rate, just like a factorial. Initially, the factorial increases at a much smaller rate, but after a particular point in time, you'll see a steep jump in the increase in the value of gamma. Probably if you are looking at x not up to 10, but let's say you are looking at it only up to 3, that is where you will see even more a better clarity picture, right? So again let me compute y. So now when you are plotting x and y, here you could see initially up to the gamma value of 1 up to x value of 1.5, we are seeing slightly different values, but after 1.5 you see that it is a kind of an increasing function. So that's one more way of interpreting your gamma function. Then once we know such kind of functions, then we are looking at another category of functions called as sigmoid functions, which are generally S-shaped. Practical applications wise, for cumulative distribution functions, we are using the sigmoid functions. So they are generally 2-parameter logistic functions. So you will have them of the form y equal to e power ax plus 1 by 1 plus 1 plus e to the power of a plus bx. Generally for logistic regression, when you are doing a logistic function later, when you are trying to understand the logistic distribution function, you will see that this is a similar kind of an equation or the density function that you would be coming across. This would have a sigmoid kind of a shape. So it is used for fitting generalized linear models, especially which have binary outcomes. So that's where I was talking of, if I have to do a prediction of a binary outcome, where I am calling it as a binary logistic regression, I can very comfortably use my logistic function. So it can work here. This is an example of a sigmoid function with 2 parameters a and b. I can also create a different sigmoid function with 3 parameters a, b, c, wherein because of a c in the power, the y can vary as per any scale. Whereas in the 4 parameters, I'll have a, b, c, d. A and B are more or less related to the locations, right? And if you are looking at left and right hand ends of the x-axis is what is given by A and B, and the scaling is given by C into D minus x. So the scaling is done by C, and the midpoint where the curve has its inflection is given by D. So by choosing my different values of A, B, C, D, I can get different kinds of shapes coming up, right? Probably if I am looking at, let's say I am setting my A value as 20, my B value, because they are minimum and the maximum, left hand and right hand ends, I'll set my B as 120, and because C is the scale, let me set it at let's say 0.75, and D value, because it's a midpoint, I'm setting it towards, let's say, 3. So I can very well compute my Y function, right? So Y in this case will come out now for different values of X, right? So let me take X again, ranging from 0 to 10 with a group of, with an increment of 1 or zero point 0.1. Now I'll compute my Y, which is the sigmoid, 4 parameter sigmoid function, which I would be writing it as A plus B minus A divided by 1 plus e to the power of c times d minus x. 1 plus e to the power of c times d minus x. So that's how I am computing the value of y. Now I am saying plot x comma y. So this is a kind of a S-shaped function that is coming up, and by changing the values of a, b, c, d, so here you see here the values are lying between 20 and 120, because the a value and b value are the left hand ends. And now when you are changing the c value, right, all else remaining the same, let's say c value instead of 0.75, I'll make it as 0.25, and based on that let me compute my y, and now let me plot x comma y. I could see that it is coming more and more flatter, right? Though now you could see, though it is lying between 20 and 120, but in reality you see majority of the values coming in the areas of 50 and 100 itself, because C is more of a scaling kind of a parameter. And even in some cases I can give negative values for C. The moment I start giving negative value of C, instead of 0.25, let's say, let me set it as minus 0.5, right? Negative value of C, and based on that let me calculate the value of y, and based on that let me get my plot of x comma y. So you are getting it completely in the reverse direction. So these are the different kinds of sigmoid functions that you can very well plot for getting a good understanding. And from a practical perspective, the Gompertz growth model is again an asymmetric S-shaped curve, which is used very heavily in the life insurance related works, demographic related works, which will have a curve like that: a into e to the power of b into e to the power of cx. So this is the shape of the function, but of course depending on the values of b and c, the shape of this graph is going to differ. You can very well take b as negative, c as positive. You can take both the parameters as negative. You'll see different kinds of graphs coming up. So this is also one more kind of a practical application that you could see, setting different values of x, setting different values of b and c, positives and negatives. You will get different shaped curves, and depending on the business logic, depending on how the output is growing, you can very well choose the parameter values of b and c, and based on that you can do the modeling of the data. So this is one more kind of a model you may want to fit to your data, right? The Gompertz growth model, heavily used in life insurance and demography related calculations. Understanding of these kind of models is very important for us. Then we also have a bi-exponential kind of a model, which is like a into e to the power of bx plus c into e to the power of dx. So it's like a summation of two different exponential kind of functions. So a, b, c, d are the parameters. Now you can actually play around. If a is positive, generally a is assumed to be positive in these calculations. But b, c, d, you can change them between positive, negative, different combinations of positive, negative. You can see how the graphs are going to come out, and that is also one more indication, because if you are seeing C is positive, which means the coefficients are positive but the exponents both of them are negative, it means it's a sum of two exponential decay curves. So there is a kind of a fast decay that is happening. If we are looking at a very quick kind of a decay that is appearing in the data, I can think of it as a summation of two, because there is one decay that is happening. First, the whole disappearing is happening, and after that, the decay actually slows down. So there is like a combination of two decays. Initially, two decays are acting together. One of them is getting exhausted, then the second one only is playing a role, so the decay will be much slower. So those kind of stuff. And if one of them is positive, the other one is negative, one is doing a decay, the other one is doing the growth, so you'll find a kind of a U-shaped kind of a curve that is coming up. Similarly, if the first one is positive, if the exponents, both of them are positive, but the coefficient is coming out to be negative, means one is increasing the stuff, the other is trying to pull it down, which means you could see a kind of a curve with a hump. So that way you can very well fit the bi-exponential models also to the data. You can actually play around with different values of a, b, c, d, take different combinations of the values of x, and you can very well plot them as well. Then we also need a few mathematical functions for our elementary probability calculations. One function we have already discussed, which is a factorial, right, which talks about n factorial. So I can very well set n factorial kind of a stuff, factorial of x. So you could see factorial of 5, which will give me 5 factorial, which is 120. So this is one more formula that we use very heavily. The other function that we generally use is choose function, which is nothing but if I have to compute ncx, I'll also write it as choose n comma x. Right? So when I'm saying choose 5 comma 3, it is 5c3, which should be equal to 10, which is nothing but 5 factorial divided by 5 minus 3 factorial into 3 factorial. So 5 factorial divided by 2 factorial into 3 factorial. So this can be written as 5 into 4 by 2, which is working out to be 10. So sometimes factorials, we have binomial distributions, various other distributions where the factorials are very much useful, whether I am talking about a binomial distribution or negative binomial distribution or a geometric distribution. I have the usage, or even a hypergeometric kind of a distribution, I require the usage of factorials and the choose functions. So it's better that I get some level of understanding regarding all these functions also to the fullest. So these are some of the basic mathematical aspects that we really need to be comfortable with before we go ahead in terms of using these mathematical functions as a part of our data analysis in depth. So just as a quick summary, we have talked about all these various aspects: the logarithmic functions, the trigonometric, the power, polynomial, gamma function, sigmoid, bi-exponential, and basic functions which can help us in dealing with elementary probability. If you have any further questions regarding the same, you can very well get back to me by giving me a call on the number that I have provided below. You can even send in an email at vamsidhar@pagegurus.com. Thanks a lot for listening to this session. Thank you very much.